Hello, everyone. My name is Mert. I am a PhD student from Boston University. Today, I'll present our recent work, Iter8 Online Experimentation in the Cloud. And this has been a joint work between IBM Research and Boston University. So let's first take a step back and drive the following example. Imagine a developer who is responsible for this recommendation system. And she studies new machine learning models and evaluates their accuracies. Finally, she comes up with this complex deep neural network model, which has a bit more latency, but comes with a higher accuracy than her vanilla model, which is served in the production. So she's like, okay, and she decides to roll out this new version to the production. And she's hoping to make things better with this new version. But how do you actually know if your new release delivers value to the customer? A key problem in this scenario is that of establishing causal relationships between the model changes or any change and the business impact. In fact, even though having higher accuracy, this new version can hurt the conversion rates in an unanticipated manner. Maybe these complex models' high latency hurt the customers, and they were not that tolerant for this delay. Here, Iter8 comes into play. Using Iter8, developers can safely and rapidly orchestrate online experiments and roll out optimal versions in an automated and statistically robust way. In our digital economy, organizations across many industries need to deliver new software faster and with better quality in order to remain competitive. As a result, we have been witnessing an increasing adoption of agile software development practice, which is online experimentation. In traditional sense, online experimentation is a technique employed to test assumptions or gain insights into new versions of your application. In web and mobile, practitioners use A/B and ABN tests where they try to identify business rewarding versions using statistical tests. However, this is not directly applicable to cloud domain because in the cloud, business results are more significantly affected by both user experience and operational concerns. For example, Amazon reported that every 100 milliseconds of latency cost them 1% in their sales. And Google reported early on that extra 500 milliseconds in search results generation had dropped user traffic by 20%. So cloud applications behaviors is inherently volatile due to performance bugs, contentions, and failures, all of which can conflate with user experience and business results. As a result, cloud poses more challenging environment for online experimentation. However, online experimentation in the cloud has been significantly ignored. When deploying the cloud, organizations need to resort to more narrow experimentation platforms. These systems provide an ad hoc experimentation where they check acceptance criteria with user-provided static thresholds. Yes, these systems may prevent a malfunctioning version by rolling it back when needed. However, they lack the mathematical sophistication necessary to assess versions correctly. And they also ignore optimization for business-oriented metrics. The release cycles of organizations across many industries has been speeding up. In particular, the recent Cloud Native Computing Foundation report shows that more than half of the organizations release weekly or more frequently, and yet practitioners lack proper solutions. At this point, we present Iter8, an open source system for cloud online experimentation. Iter8's hybrid model provides wide variety of experimentation types and goals, and Iter8 encapsulates our mathematical framework built on online Bayesian learning, which provides statistically empowered experimentation. Iter8 is devised specifically to tackle various key challenges posed by the online experimentation in the cloud domain. So let's walk through these challenges. First of all, in addition to business reward as done in the web and mobile domains, the cloud applications are expected to satisfy service level objectives, SLOs, typically expressed in terms of performance or correctness metrics, such as limits on the tail latencies or error rates. In Iter8, our mathematical framework holistically incorporates both SLOs and business reward. And second, In web and mobile domains, the distributions of users across competing versions is decided a priori and fixed for the experiment duration. However, in the cloud rollout, it needs to automatically adjust the user traffic split across the versions as more data becomes available. Our novel multi-arm bandit algorithms intelligently adjust the user traffic among the competing versions. And finally, a cloud experimentation system must exhibit two fundamental properties, which are accuracy and repeatability. And our system is based on statistically rigorous analysis of data accumulated throughout an entire experiment. So let's walk through how does Iter8 orchestrate online experiments. A practitioner starts an experiment by creating an experiment spec. On the right-hand side, you will see an example of the experiment spec, on which she declares the application and the competing versions. She determines objectives such as limits on the tail latency or the business rewards. And finally, she determines the strategy which is to maximize reward in this experiment. The experiment spec is then represented in Iter8 as a multivariate utility function. Why? Because first, it combines multiple KPIs into a single utility function such that it can be learned and optimized online. And second, it enables ranking and comparing different versions. Iter8 then associates a Bayesian belief distributions with each utility. As the experiment proceeds, these belief distributions converge to their true values. For example, on the figure, we see belief distributions after 10 samples versus on the right, we see belief distributions after 400 samples. At every iteration of the experimentation, Iter8 faces a fundamental trade-off between exploration versus exploitation of the versions when deciding how to adjust the traffic. Multi-arm bandit problem well exemplifies this trade-off. In multi-arm bandit, gambler goes into casino and she wants to maximize her revenue while learning about all slot machines in the casino. So building on the multi-arm bandit, we developed two new algorithms. And a PBR algorithm quickly maximizes traffic towards the best version and hence maximizes the reward during the experiment. It is essentially inclined toward exploiting the best version according to the belief distributions populated so far. Whereas PBR split works on maximizing confidence towards all the versions, can hence find the best version quickly. So it is essentially inclined toward exploring all versions to evaluate and maximize confidence, and then which will help to identify best version earlier with a statistical confidence. Iter8 essentially enables online experimentation of applications running on any cloud based on Kubernetes. Iter8 exploits APIs for traffic management such as Istio to distribute users across competing versions. And architecturally, we have two components. On the bottom, you see Iter8 controller, which orchestrates all ongoing experiments and utilizes APIs for traffic management. And on the top, we see Iter8 Analytics, which is the brain of our project. It encapsulates Bayesian learning along with the bandit algorithms. We next present our evaluation. So we conduct our experiments on a 14-node Kubernetes cluster in a multi-tenant public cloud. Our cluster has various worker node flavors with various CPU resources and GPU nodes for the machine learning model serving. We use Istio for the traffic management and Prometheus as a telemetry database, and we use two benchmark applications, microservice-based and the machine learning model server. We first study the accuracy in online experiments. In this one, we deploy a new version in train ticket application, in particular travel service, and perform Canary rollout. We compare Iter8 against Argo rollouts and Flagger. In Canary, we slowly roll out new version while making sure that it satisfies all of the SLOs given. We vary the experiment conditions such as the durations, various SLOs, and different load intensities to the application. And finally, we define accuracy as the ratio of correct experimental decisions over total number of experiments. In the summarized results, we see that Canary releases orchestrated by Iter8 result in correct outcomes 93% of the time and substantially outperforming alternatives. Next, we study a scenario where practitioner wants to maximize business reward subject to operational constraints or SLOs during an experiment. Argo rollout and Flagger do not have the reward concept, hence we switch our setting in this experiment. Our experimentation is now a machine learning model selection, where the code running is a machine learning model, and we have 5 representative large deep neural network models that are competing with each other. We compare our algorithms against XP3, which is enabled by the state-of-the-art machine learning serving framework Clipper, and we further implement our own version of the XP3 in order to incorporate SLO concept into it. And also, we have another baseline algorithm or heuristic UNIF, which is a baseline policy where traffic is equally distributed among versions. And we set reward equals to the model accuracy just for demonstration purposes. And in this one, we are trying to maximize this reward. And the results summarized from multiple runs show that our PBL algorithm quickly shifts traffic towards the best version. In particular, it keeps traffic to the optimal version 93% of the time cumulatively. While doing so, it maximizes the reward by up to 8%. Next, we study a scenario where practitioners' aim is to find the best version as quickly as possible. We keep the experimental setting and the problem we study same, and in this scenario, PBR split comes into play. Essentially, results summarized from the variance runs show that PBR split reduces total number of requests by up to 60% compared to alternatives, which enables practitioners to end experiments significantly faster or earlier. In this talk, we presented Iter8, an open source online experimentation system for cloud. Thank you very much for joining and listening to my talk.